I've got the green spinny thing, and I'll take these quarters, and they're going to go around. Are both quarters accelerating
Yes.
as it goes around?
Yes.
Why are they accelerating?
Because it's turning.
And it's not traveling in a straight line. Okay? So the question being is that what's the source of the force that's allowing them to accelerate?
Friction.
Yeah, friction, right? Okay. So if you look at when I had that rubber stopper, and it's the same thing here, going around in a circle. So in the lab tomorrow, which we're going to start tomorrow and finish up on Thursday, you're going to calculate how fast that rubber stopper is going as it swings around. So, where's my rubber stopper?
Sorry, Preston. We're all going to be gone for the lab.
So, as I take this rubber stopper, and this is what you're going to do in the lab, and I swing this thing around, I need to figure out how fast that rubber stopper is moving. So, Gap Sean, what's one thing that I can measure?
The entire time.
Huh?
I don't know the time it takes to do one rotation.
Okay, I can measure the time it takes for it to go around once. Now, we're going to use uppercase T. We're going to use uppercase T for something that returns back to the same point. Like, for example, the comet, okay, that's visible in the western sky. The orbital period for that comet is about 80,000 years, give or take 5 minutes. So what's cool is that the last people that would have seen that comet were probably the Neanderthals, 80,000 years ago, okay? So that takes a long time for it to go around. Conveniently, our Earth has an orbital period of
365.
365 days as we go around the sun, okay?
Yeah.
How long does it take for the Earth to spin once on its axis?
About 24 hours.
24 hours. So anytime you see uppercase T, you're talking about something that's going to return back to that same point. So I can measure the orbital period, okay? I can measure how long it takes for this thing to go around one time. Well, what's another thing that I can measure? Colin, I think, is willing to throw you a bone.
The radius.
Oh, I can measure the radius, okay? So if I measure the radius, what could I determine from the radius?
Diameter, circumference.
The circumference.
Area.
Let's go with circumference. You're right, I could get the diameter. That's valid, okay? It just wouldn't do me any good.
Area.
I could get the area too, really don't care. How about circumference? Okay? So, circumference is,
2 pi r.
okay? So, when I look at this to get the velocity, all this is distance divided by time. So 2 pi r over t is nothing more than distance divided by time. Now, the three of you, what's the only time you can use distance divided by time to get a velocity?
Constant velocity.
Yes.
Yes.
So, this is where we're going to do a little bit of hocus pocus. So if you look at v equals 2 pi r over t, as these two quarters go around, okay? So, as these quarters go around, like this, which quarter takes longer? The outside quarter, the inside quarter, or is it the same?
The same.
The same.
Exact same, okay? They're both, if you time them, they would both take the exact same amount of time. Which one is going to have the greater velocity?
Outside one.
The outside quarter or the inside quarter?
Outside quarter.
Outside quarter, why?
It's going to travel greater distance.
In the
Same amount of time.
same amount of time. So the quarter on the outside is going to have a greater velocity because it's just like running on a track. If you're on the inside track, you have the advantage because of the fact that you're traveling a shorter distance. So the quarter on the outside has the greater velocity. So now we're going to do a little bit of hocus pocus. So we just said that centripetal acceleration equals v squared over r. Okay, so this is always kind of like the pirate's favorite unit because it goes into R a lot. So here's the story. We just said that V equals 2 pi R over T. So could I take 2 pi R over T, put that in there and square that, and then divide by R?
Sure, absolutely. Go for
Absolutely.
it.
We're good with it, right? Okay? So I'm going to square this whole thing, and I'm going to get 4 pi squared R squared over T squared over
R.
Now, this is where the pirate gets sad. Why?
Your R's.
Oh, I'm going to lose one of the R's.
R.
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 So I get centripetal acceleration equals 4 pi squared R over T squared. Cool. Now, this is not on your equation sheet. You need to know it. It is easily derived. You take 2 pi R over T, you substitute that in, you square it, you get 4 pi squared R over T squared. Now, Preston, do I still get the correct units of meters per second squared? Yes, because what's the only units that are on the top?
Meters.
And then I'm going to divide by T squared. Okay, so I get meters per second squared. If it doesn't, the equation doesn't work. Now, we just said that mu equaled AC over G. So here's where we take this to the next logical step. As I spin this up and make it go faster and faster and faster, which quarter will fly off first?
The outside one.
The outside quarter, the inside quarter, or will they both fly off at the same time?
Both fly.
Cohen, what was your statement?
The outside quarter.
Why?
Because it has more, like it's moving faster.
So that's more inertia.
Yeah. No. No, don't say that.
Yeah.
I feel tricked. I was trapped. No. The inertia
Do
is,
both quarters have the same inertia?
yeah. But
You said that with no confidence.
no, yeah, they
Why do they have the same
have
inertia?
the same amount of stuff.
Okay, they both have the same inertia.
The outside quarter should fly off first because it's experiencing more force.
Why?
Because it's moving faster. The rate R is bigger. R is bigger,
And this
so
period is
smaller, or the same. The same.
same for both,
The same. So
Here it is,
bigger
same
over
for
same
both.
equals bigger,
right?
and bigger over gravity equal.
Is there a limit to what the frictional force can do?
Yes.
Yes, just like there's a limit to what I could do with this string. I promise you I could not take this string that I can just take and pull apart very easily and try and swing Hank around on the outside of this string. It's not going to happen because there's a limit. So there's a limit to what friction can do. It can only provide so much force. And once you exceed that limit, it's going to go flying off, right? So if I spin this up, oddly enough, that first quarter goes flying off because of the fact that it exceeded the frictional limit first. Okay. Now, here's another handy thing that you can do. So over here on this yellow sheet, and we've talked about this before, briefly, you have this equation that says period is equal to the inverse of frequency. Now, period is technically seconds per revolution. We never put the revolution part on there, but it's always implied, okay? So like in the lab, you're gonna measure, hey, how long does it take to move one revolution? So, frequency, if you solve for this, so notice that these are inverses of each other. So if I solve for frequency, I multiply by frequency, divide back, I get 1 over t. So if you look at the units, period is seconds per revolution. So the revolutions are going to flip up, and you're going to get revolutions per second. Okay? A lot of times that's written just as 1 over seconds, or sometimes it's just written as s to the negative 1. once we study light and electricity, we're gonna call those hertz, which is how many revolutions per second is going to happen. So, now notice that these are inverses of each other, and here's the classic demonstration. So if I move this thing rather slowly, okay, it takes a long time for it to go around. But it's not going to make many revolutions per second. But if I make it go faster, what happens to the amount of time for one revolution?
Goes down,
It goes down, but what happens to the number of revolutions?
goes up.
It goes up. This is why these are inverses of each other. So sometimes, and this is the math, the magic you can do, we said that centripetal acceleration was v squared over r, which is also 4 pi squared r over t squared. We said v equals 2 pi r over t. So can I come in here where there's a t and put 1 over frequency?
Yes.
Yep.
Certainly, I can do that. Come on, erase, go away. So if I do that, then I get
2 pi r f.
or v equals 2 pi r times
F.
frequency. Okay? Now, could I do the same thing over here? Could I write that as 4 pi squared r 1 over f squared?
Yeah.
And that becomes 4 pi squared r
F squared.
f squared. So one of the things that you have to watch in the problem, are you given frequency or are you given period? Okay? So a lot of times we'll talk, if you've ever seen like a tachometer on your engines run at revolutions per minute. So if you have like, say 1,000 RPM, which stands for revolutions per minute, okay? Is that frequency or period?
Frequency?
That's frequency. It's how many revolutions per minute the engine is making. But can you operate in minutes?
No.
No. But what you could do is change that into 1,000 revolutions per
60.
60 seconds. And then you can get your frequency and then you can go from there. Okay. So I know you all have to head out, so let me go over some things with
This looks like a full size.
It's only one page though.
No
It's gonna be
backside
full
is
on.
one.
Yeah, no backside, but like, it's still 11 on the front.
That's not too bad. There's no back.
3 multiple
Okay.
choice.
This is really looking like a 4 hour.
So, let me give you some hints.
That's enough to
So,
Potentially.
when you get down to this first question, number 3, and by the way, where are you not gonna answer any of these?
On the paper.
this piece
This
of paper.
piece of paper.
No,
So,
that piece of paper.
if you look on question number 3,
Yellow sheet.
you got, it's made to go faster and wires played out until both the speed and the radius circle are constant at double their original values. So again, you can do this one of 2 ways. You're gonna look at v squared over r. So what's an easy velocity you wanna use if you introduce smash mouth physics? 1. 1 meter per second and a radius of 1 meter. Oh, okay, boom, there you go. Now, then, you're gonna make it go faster as more wires played out until both the speed and the radius are constant at double their original values. So now, AC prime is gonna be, instead of 1 meter per second, you're gonna have it at 2 meters per second, but that's going to get squared. And then instead of dividing by 1 meter, I'm gonna divide by,
2 meters.
so that's gonna get you
2 meters per second.
2 meters per second squared. So what's gonna happen to your acceleration? It's gonna change. It's gonna be different.
It'll be new.
Now, if you want to do the elegant approach, otherwise known as the Collin approach,
I don't even do that. I normally do smash mouth on that one.
so you're gonna have 2v squared over 2r, which is gonna get you 4v squared over 2r, which is gonna get you 2v squared over r. That's the other way. So don't forget, there are questions out of your book. When you get to question number 10, let me give you the visual. So here's this centrifuge. If you've never seen a centrifuge, it spins test tubes really, really fast. And so what's happening is that this 30-degree angle is with respect to the vertical. Here's your center spin axis. You have to find the distance from the center spin axis out to the bottom of the test tube. Okay, go be free.
So,
Just change it to D. Let's just
I
say
know,
that-
I wanna know how I'm wrong though, so I can actually understand.
What do we do?
Oh, it's still recording.